Hi there. Welcome to another lecture with Chem Coach Powers, and we are talking about chemical reactions. We're in chapter 7. We're hitting chapter 7.1 today. So let's go ahead and learn about what our objectives are today. First objective is to describe what happens in a chemical reaction, then to identify the different symbols we use in a chemical reaction, to recognize the evidence that would support that a chemical reaction is taking place, and to describe the differences between endothermic and exothermic reactions. So let's start with this chemical reaction here. Chemical reaction in definition is a process in which substances change into different substances. We're starting with something called hydrogen carbonate, which is basically two hydrogens with a little carbonate group to it. And now this is carbonic acid, okay? So this is something that is going to be found in your sodas. And when you have soda, the carbonic acid is slowly changing into H2O and CO2. And so the little bubbles that you see in your soda can, that's the carbon dioxide, and that's after it's gone through a decomposition reaction and changed from the carbonic acid into water and CO2. So this is a chemical reaction. Now notice that there are two hydrogens here, two hydrogens here. There are one C, or there is one C, and one C there, one carbon and one carbon. There are three oxygens on this side, and on this side you have one oxygen, and then you have two oxygens, right, for a total of three oxygens, all right? So you have the same number of atoms on both the left side as the right side of the reaction. Now that's important because that is something that's helping us to understand that the law of conservation of mass is indeed taking place and is supported here. Now, the reactants are the things on the left side of the reaction. So over here we have our reactants. And in this case, we just have one reactant, and it's the carbonic acid. And our products on the right side of the reaction, as we have two of them in this case, carbon dioxide and water. Products are the substances that are being formed. Reactants are the substances that are participating in making something new, right? The things that you start with, the starting materials that are going to be made or transformed into something new. So again, atoms are not created or destroyed here. They have the same number of atoms on both sides of the equation. That's important to understand with a chemical reaction. Let's talk about some of the symbols that are important in a chemical reaction. We have these arrows here, and that means to produce or yield. Okay, so if I'm making something, I'm getting a certain amount of yield of a certain chemical. That would, be the word we might use there. S is for solid, and we put these in parentheses. L for liquid, G for gas, and AQ for dissolved in water. Now let's look back at that previous equation and see what we have. You notice that we have the AQ here. This means that this carbonic acid is a substance that's been dissolved into the liquid. And after the reaction takes place, we get a liquid and a gas. Okay, so those are the states of matter that are being shown there. Now, we also have an arrow, and sometimes, a delta sign, a triangle. Sometimes we take that delta sign, we put it over an arrow to signify that we had to heat this material to actually get it to react. And then sometimes we're going to put an element or a compound above our arrow, and that indicates that a catalyst was necessary for this reaction to take place. So in this case, you might have like a catalytic converter needs platinum in order for the reaction to take place. The other thing, which I think is kind of obvious, but I'll go ahead and include it, is the plus sign. The plus sign basically means we're mixing them together, or they're together in a combination of some sort. Sometimes they're going to be reacting, and sometimes they're going to just be in a mixture. For instance, on this side, that plus sign that you have here is basically saying, hey, these things are mixed together. We have carbon dioxide and water together. If they had been on the reactant side, we might have been saying, hey, you know what? These things are actually interacting and becoming a new, product, and so they're actually chemically, interacting in that way. So let's talk about the different evidences that we have for a chemical reaction. This first one is probably one of the most significant. It's a release of heat, electricity, sound, and light. Now, when do we see these types of things? Heat and fire, electricity, car batteries, Sound, you hear like little explosions, right? Light, the light that's given off in a firework or in a fire, things like that. So release of energy, absorption of energy could also be another great indicator of a chemical change, but we don't usually think about absorption of energy as much as the release of it. Then we have color change. Okay, now why do we put the word dramatic in front of it? Well, because color change doesn't necessarily mean that you're going to have a chemical reaction, but most of the times we talk about it, it does. And so it's going to be significant. You can think about the leaves as they change color, right? They're losing their chlorophyll. Chlorophyll is being broken down. And so in this case, because chlorophyll actually breaks apart, then we can say, hey, chemical change is taking place. That's why it's not green anymore. Evolution of a gas, okay, that's just releasing gas. So things like your soda pop is going to have carbon dioxide in it. And then we have this interesting word here, formation of a precipitate. Now, this is a word that is not connected with precipitation in terms of, hey, rain falling, right? No, that's not what this is about at all. If we take two clear solutions and we mix them together and all of a sudden we get this cloudy substance that comes out of it, what happens is if you let that water evaporate and you see what's left over, that cloudy substance is actually a solid powder. And so we're actually forming solids out of liquids. Now, what does that mean? Well, we take two soluble products. So some things are soluble and some things are dissolved, right? So these things that are soluble are dissolved. And so these clear solutions, that means something's dissolved in them and a chemical is dissolved inside of them. But once you put them together, then one of the products of their chemical reactions is insoluble. So now we have something that's not dissolved, and that's what falls out of solution. That's the precipitate, the insoluble product of a chemical reaction. Okay, so what's the best evidence? Well, really, we want to see, did we create some new properties, all right? Different identification properties or different characteristic properties. If we have a new substance that has these new properties, then we have a chemical reaction. Now, sometimes we can't see that with our naked eye and we have to do various different tests on it, but that is the best way that we can tell for sure that a chemical reaction has taken place. All right, so let's look into energy and reactions in a little bit more detail. First of all, let's make sure that we realize energy is always involved, okay? So we have all energy always involved in a chemical reaction, okay? And so you're either going to be giving off energy, you're going to be absorbing energy, and really you're doing both to different degrees. Let's talk about what happens as we break bonds. Energy is added as you break bonds. Okay, you have to put energy in to break the bond. Let's imagine a little carbon here, and carbon's with another carbon. And in order for these carbon bonds to break and have the carbons be their own little carbon pieces, then you have to put energy into that. Once you put energy into that bond, then you could have, boom, it could break, and you could have these two carbons flying around separately on their own. Okay, most forms of energy can be used to break bonds. Let's talk about a few of them. Let's talk about heat. All right, so if we have fire, right, imagine a fire, and you're taking, for instance, glucose. Maybe this is a carbohydrate, cellulose, something like that. But let's just take the basic structure here, C6H12O6. We take that basic structure of cellulose, for instance. Cellulose is made up of a bunch of little glucose molecules, and you add fire, you add energy, and that's going to break up those little carbon bonds, just like I was talking about here. Those 6 carbon bonds, the hydrogens, the oxygens, that's all going to break apart, and it's going to form some new molecules. A good example of electricity breaking apart substances is this word called electrolysis. And electrolysis is basically electrocuting water. You take a battery, you take a 9-volt battery and stick the head in a little bit of salt water. You'll see this happen. It's H2O being transformed into H2 plus O2. Okay, and so this is a liquid that's transformed into gases. You can collect these gases on the ends of those terminals, and that's a flammable gas, and oxygen can help to accelerate that flammability. And so it's kind of a fun thing. You can quick and easy collect some hydrogen gas. Takes a while, but pretty cool. Sound can break bonds as well, and light. You think about one of the good examples of light is O3, that's ozone, and if you are adding UV energy to O3, you're going to break apart the bonds and you're going to form some O2. And so here's a good example of light actually coming through and being enough energy to break chemical bonds, and so the chemical process is taking place. So let's look at the releasing of energy by forming bonds. Okay, so what we have here, oops, let's go back to that one there. We want to focus in on the bonds that are forming because they're getting to a lower potential energy state, and so they're releasing energy. Okay, so remember that bonds form to become more stable typically, and they're becoming more stable. They're basically going to have a lower potential energy, right? So lower potential energy is kind of what we're going for here. And so when you go from a higher potential energy, imagine yourself like on a cliff and woo, fall off that cliff. Okay, you go from a higher potential energy state to a lower potential energy state. And this is making the bonds more stable. Okay, and the amount of energy that you fall down is basically the amount of energy that's given off. And so in any type of bond formation, breaking, you're going to end up having some energy loss, some energy gained. And if your overall energy lost is greater, then it's called an endothermic reaction. If your overall energy gained is greater, that's called an exothermic reaction. So we'll talk about that in the next slide here. But we got chemical energy then that can be defined as the energy released when a chemical compound reacts to form new compounds. There's going to be energy released, and then sometimes it's going to be absorbed, right? If you need to have energy added in and stored. And that's kind of what happens if you think about it. That's what happens when you take oxygen in the atmosphere, and then you take, the carbon dioxide that's in the atmosphere. This is what plants do, and they store it, into that glucose molecule. Then what's happening is you're taking something that has lower potential energy, the oxygen and carbon dioxide, and you're storing it into something. And so you're basically taking and oops, I'm going to try that again. Actually, I'll tell you about that here in a second as we talk about the exothermic stuff as well. But remember this little formula, because we're going to come back to this, that part right there is storing energy into bonds, okay? And going the other direction is going to be releasing the energy. Okay, so total energy that exists before the reaction is equal to the total energy of the products and their surroundings. In other words, energy is oftentimes lost as heat, but we are not losing energy. Just like we're not losing atoms, energy is going to be transformed into heat, and then it's going to be unavailable for reuse. So we sometimes say lost as heat, but as heat means that it's still energy. And so energy is not gone forever, it's just transformed. And heat now is the unusable form of that energy oftentimes, okay? So energy is never created or destroyed in these chemical reactions. All right, so here would be kind of like a visual way of looking at these types of reactions. We have octane. In this case, we're talking about isooctane. Now, this is basically the same stuff that is in your gas tank in your car. Octane, you've heard of high octane fuel, right? And so gasoline is basically octane, or at least that's one of the main components of it. And so if you take that octane, you react it with oxygen, you're going to form two products, right? So these are your reactants on the left, and then these are your products on the right. You're going to form carbon dioxide and water. And then you're also going to form energy. Now, this energy is the energy that allows your car to move, right? Because that explosion of gas inside your piston is what causes the car's engine to allow for the wheels to be turning over. And so in a reaction where you've got some gasoline, you are going to be breaking those bonds. And so going from this place where you have all of this stuff together here and breaking it up into a whole bunch of small little pieces. Notice we got the greens in there and the greens are in here, right? The oranges are here, the oranges are all around in here. And then you get water as well. So there's an orange and then there's the blue. The blues came off of over these things as well. So you take and rearrange the atoms, and energy is the product, and this is what gets your car to work. Okay, so it's pretty cool. All right, so let's talk about exothermic and endothermic reactions. Now, exothermic reactions are reactions that release energy. Okay, so release energy is exothermic. And then if it is going to absorb energy, it's going to be endothermic. Now, you guys have heard of ectotherms and endotherms probably from life science, but the endotherm is different than endothermic, okay? Whereas an endotherm might be a warm-blooded animal, the endothermic processes are processes that are absorbing energy, okay? So different terms And so don't think of them as the same type of thing. Endothermic reactions end up having more energy necessary to break the bonds than forming the bonds, okay? So it's more to break than it is to form. And so that's endothermic. Exothermic is going to end up being exactly the opposite, okay? They're going to have more energy in the releasing, okay, there's going to be a lot of energy released as they form the bonds compared to when they're breaking bonds. So it's taking less energy to break the bonds. So more energy is given off in forming bonds than in breaking bonds. Okay, so you see how they're kind of the exact opposite, right? And it's all about bond formation, energy bond formation, and bond breaking. And it's all a net play in and out of that, okay? Remember that exothermic reactions, they're going to have the energy lost as heat or given off as heat. And then in endothermic reactions, these are going to be an overall energy input. Now, you're familiar with some of these already. If you guys have ever seen like an ice pack where you hit that little ice pack, it's got stuff inside, you pop it, and all of a sudden it gets cold. Well, that's an example of an endothermic reaction. And look at these graphs. These graphs are showing us a couple things. Now, this is the amount of energy over here on the left. So think of this as potential energy. So this is the potential energy of my reactants. And it's not very much potential energy. And as I go through, I'm storing energy into the bonds. Okay, so this is an example of taking something and storing energy into it. So if I have, for instance, CO2 and H2O, okay, and I want to take that carbon dioxide and I want to put it and store the energy into sugar. Okay, that little line there wasn't supposed to show up. It's a spontaneous little line. Go away. This is a process. This is endothermic. This is why you need sunlight to get this process to take place. That plants are taking in the sunlight and they're absorbing that energy and they're storing it into chemical bonds. And so this is where our products have a higher potential energy than our reactants. Now, this is still stable. The glucose molecules that make up, the material that is inside your body, those are still stable molecules. They're just not as stable as the original reactants. Carbon dioxide, water, those are actually more stable than the glucose. However, glucose is still plenty stable. It's just that we went through a chemical transformation to store energy. Now, once we have that energy, we can go back over here to the exothermic reaction, and we can think about what happens there. We have C6H12O6. In other words, you're eating, the food that you're eating. Your body is taking that, and inside your mitochondria is breaking that stuff down. So my reactants have a higher potential energy, and then it takes a little bit of energy to break that stuff down. This is area right here between here and here. That's called the activation energy, okay? So activation energy, you're going to see that on the next slide, but activation energy is the amount of energy it takes to go from your original potential energy state and go over that top of that little peak, and then you're going to end up having energy release. And energy release is even more than the activation energy. And so this whole area between here and here is all of the output that you're going to get that's going to feel like heat. And so in your body, this is actually going to be, the amount of extra energy you have. You can start making ATP that's going to be able to move your muscles and things like that, right? And so this is something where in this particular example, you go from C6H12O6, you're going to be breathing out the carbon dioxide. And of course, you had oxygen that was helping to break all this stuff down. But you're breathing out the carbon dioxide, and you're going to be creating this ATP, and that is going to be an exothermic reaction. And so your body is going to get warm. As you're breaking things up, the reason that your body has this temperature all the time, because your body maintains this homeostasis where it continues to go through these reactions, and it's continuing to give off heat. And so your body is warm because it's going through a chemical reaction, which is really cool. Okay, so other examples now, if we want to talk about, like, obviously we talked about the endothermic being the ice pack. We talked about fire being a great example of an exothermic reaction, but even thinking about our body and how our body is going through respiration, right? That's that process where we're breaking down sugar, and we are going to be creating new carbon dioxide molecules and a lot of extra energy to make ATP, that kind of stuff. Those are good examples of exothermic reactions. Also, if you thought about ice packs, you might have also been thinking about hand warmers. Hand warmers are great examples of exothermic reactions as well. And there's a couple different types. One of them uses like sodium acetate. The other just uses iron that gets exposed to oxygen, can kind of be reused. Sometimes if you use the sodium acetate one. Okay, so look at one other thing here. I want you to pay attention to where energy is. On the left side of the reaction, if the energy is in the reactants, that's going to be the endothermic reaction where it's absorbing energy. If the energy is in the products, that's going to be the exothermic reaction where it's in the releasing of energy process. Okay, so we've learned a lot of good things in here. I told you we would talk about activation energy. Again, it's that amount of energy that's required to go from here, wherever that base potential energy state is, all the way up to the peak where it can finally go and start moving along down here. Now, what's happening at the molecular level as we're seeing this happen? Okay, so remember that down here we might have had the carbon-carbon bonds. And as I'm putting energy into it, these carbons are getting a little bit further apart from each other, right? I'm putting energy in to break the bonds, and so that's kind of moving them apart. And after they get to that point, then they're actually able to break apart and then reform. So now this carbon might be able to form with maybe CO2, okay, and then form with oxygen to make CO2. And so down here we have a more stable state in that case. Okay, so the activation energy again is the minimum starting energy, and that's that little gap that I have right there. And again, a good example of this, when you strike a match, you are striking a match and you are going to put amount of energy in as you move that match head across the box. That's the amount of energy that you want to put in to get the reaction started. And after that, the reaction kind of proceeds on its own. Okay, so let's wrap it up and see what we learned. Okay, can we actually, do these things that we are talking about? All right, so can we describe what happens to atoms in a chemical reaction? Yeah. Remember that these atoms are being rearranged, okay? And they're going to form new compounds, new substances with new unique characteristic properties. We looked at a lot of different symbols that are used in a chemical reaction. We looked at the gas, we looked at the liquid, we looked at the solid, we looked at the aqueous. Well, it almost looked like a Q. We looked at pluses, we looked at arrows, we looked at little delta symbols. We looked at little substances that were above arrows. Now we can identify what all those different things are, right? Evidence that a chemical reaction is taking place. We went through a whole list of them, right? Things like giving off gas, changing color, that kind of stuff. Describe the differences between endothermic and exothermic reactions. So now we can, again, describe that. Endothermic is absorbing energy. It's going to get cold if you touch it because it's going to pull the heat out of your hand. Exothermic reactions are releasing energy, and it's going to be hot to the touch because it's exuding energy out from it and putting that energy into your hand. So I hope you enjoyed learning about the basics of chemical reactions. Some pretty good stuff there. We will catch you later. God bless you. Have an awesome day.